There's a clock tucked deep in Earth's core that hasn't struck in 780,000 years. And it may be winding toward another quiet alarm, a metronome of molten iron and motion, steady, patient, unseen. The sun resets its magnetic poles every 11 years, as casually as flipping a switch. We're still living under the same polarity our ancestors carried while they were dodging saber-toothed cats. But in May 2024, something changed subtly, but unmistakably. A solar superstorm hit Earth. Our magnetic shield compressed like never before, and 5 days later, it still hadn't fully recovered. As if the shield was slow to exhale, scientists are choosing careful words, the kind that says they're concerned but don't want to spread panic. Stay with me, because the day North becomes nowhere is a story no civilization has ever had to live through. If this mystery has you as spellbound as it has me, subscribe so you'll hear when we follow what happens next. Step by step. In the dark. Leave a comment with where you're watching from, your time zone, and whether you think we're truly ready for what a magnetic reversal could bring. Part 1. The storm that changed the conversation. On May 10th, L'Antenling Archeseur. Something that felt impossible happened. The kind of headline you'd expect in a sci-fi novel. Auroras showed up over Florida. Not faint green whispers at the horizon, but full curtains of light silk rippling through the night like a storm-tossed flag. Colors sliding over clouds with eerie calm. People in Kenya stepped outside and saw it too. So did observers in northern Chile. These weren't places that occasionally glimpse auroras during strong solar events. These were latitudes that, in recorded history, had never seen them. The Mother's Day geomagnetic superstorm had arrived. Rated G5, the highest level on the scale. A label reserved for the rarest kind of geomagnetic fury. Scientists expected solar cycle 25 to be mild, maybe even dull. Instead, the sun threw a punch that overshot every forecast model. But here's what most people missed while they were taking selfies with the sky. The storm itself wasn't the strangest part. The strangest part was what it did to Earth's magnetic field, not in a headline way, but in the quiet numbers beneath the spectacle. Let me put it in an image you can hold. Picture Earth wrapped in an invisible bubble, a protective shell of magnetic lines stretching from pole to pole, curving outward into space. That bubble is the magnetosphere, and inside it is another structure called the plasmasphere, a donut-shaped region of charged particles hovering just above the atmosphere. Faint as a halo you can't quite see, the plasmasphere acts like a cushion, soaking up energy from the solar wind and helping keep our planet safe from the harshest space weather. It's always there, quietly doing its work. During the May storm, that cushion was compressed by 80%. 80. The plasmasphere was shoved inward like a tin can under a boot, pushed so close to Earth that low-orbit satellites suddenly found themselves outside our primary magnetic protection, exposed to harsher currents. This wasn't supposed to happen. Strong storms can squeeze the magnetosphere. Yes, but not this far, and not with pressure that stays this steady. The solar wind hammered Earth's magnetic field for hours, and the shield buckled inward in a way that made veteran space physicists go silent when they saw the plots. But compression wasn't the real problem. The real problem was what came after what the system couldn't do quickly anymore. Normally, when a geomagnetic storm passes, Earth's magnetosphere rebounds within 24 to 48 hours. It snaps back like a rubber band and the system returns to baseline. After the May storm, it took 5 days. 5 days for the plasmasphere to reinflate. 5 days for field lines to loosen back into their usual geometry. That's not a rebound. That's a limp. The kind you notice only after the adrenaline fades. And scientists began using a phrase they don't use lightly: structural fatigue. When you stress a material again and again, it doesn't always return to its original shape. Metal bends, rubber loses elasticity, and, it seems, planetary magnetic fields can show wear as well, quiet fatigue written into invisible lines. The magnetosphere is supposed to behave like a shock absorber flex under pressure, then spring back, resetting itself for the next hit. But if that shock absorber doesn't spring the way it used to, It suggests something inside the system has changed, something fundamental. This wasn't only about the storm being unusually strong, though it was about the response being unusually weak. It's the difference between getting hit and falling versus getting hit and realizing you can't stand back up as quickly as you once could. That second outcome hints you were already compromised before the punch even landed. Now, I want to separate what we know from what we're guessing. The compression and the recovery time are verified, measured in hard numbers. Multiple agencies recorded them. The plasmasphere did take 5 days to stabilize. And that does exceed historical norms for storms of comparable intensity. What remains speculative is what this says about the long-term integrity of Earth's magnetic field. Was this a one-off anomaly, or the start of a pattern? Is the magnetosphere losing its ability to recover because Earth's internal magnetic engine is weakening? Because here's the thought no one wants to say out loud. Even in a laboratory, if the shield didn't bounce back properly this time, what happens during the next storm and the one after that? If each hit leaves the magnetosphere a little more compressed, a little slower to recover, then we're not talking about isolated events anymore. We're talking about cumulative damage. We're talking about a system being pushed toward a threshold it may not return from. And if you think the May storm was a freak occurrence, some cosmic coincidence we can shrug off, then you haven't been watching what Earth's magnetic field has been doing over the last century. Because while the sun was throwing punches, Earth's defenses were already cracking in ways that have nothing to do with space weather. The magnetosphere isn't just getting tired, it's getting lopsided. Part 2. Earth's magnetic armor is no longer symmetric. When you imagine Earth's magnetic field, you probably picture something clean and orderly. 2 poles, north and south, with field lines arcing smoothly between them like the diagrams in textbooks. A perfect dipole stable. Symmetrical, the way a bar magnet looks when you sprinkle iron filings around it. That image is comforting because it implies predictability. It implies control. And that image is no longer fully accurate. Earth's magnetic field isn't weakening evenly. It isn't thinning in a gentle, uniform way that grants us centuries to adjust. Instead, it's cracking asymmetrically, developing weak spots and bulges, twisting in ways that challenge every assumption about how slow and graceful pole reversals are supposed to be. The clearest example of that broken symmetry sits over the South Atlantic Ocean, a region scientists have watched for decades. It's called the South Atlantic Anomaly, and it's getting worse. The South Atlantic Anomaly is exactly what it sounds like, an area where Earth's magnetic field is significantly weaker than it should be. If you mapped field strength across the planet, most regions would fall within a familiar range. But over an oceanic stretch between South America and Southern Africa, the strength drops to less than half of what it is elsewhere. It's a dent in the armor, a soft spot in the shell, and it has been expanding for more than a century. Satellites feel it first. They pass through that weakened patch like a boat crossing thin ice still floating. But listening for cracks, when a satellite passes through the South Atlantic Anomaly, it enters a zone where cosmic radiation exposure spikes. Because the magnetic shielding is thinner, engineers have learned to live with this. They program satellites to power down non-essential systems while crossing the anomaly, reducing the odds of electronic damage. Some satellites effectively dip through that region, suffering more radiation-related glitches and errors than anywhere else along their orbit. This isn't a guess. This is routine operational reality. So why does it matter for pole reversals? Because symmetry is a signal. When a planetary field is stable and strong, it behaves like a dipole. 2 poles, clean geometry, predictable behavior. When a field becomes unstable and weak, it starts to deviate. The dipole wobbles. Weak zones appear. The field becomes multipolar, meaning instead of 2 dominant poles, you get several smaller magnetic nodes scattered around the planet. And that multipolar state is exactly what Earth's field looks like during a reversal. The South Atlantic Anomaly isn't just a weak spot, it's a preview. Now let's talk about the poles themselves, because they aren't sitting still either. The North Magnetic Pole, once drifting slowly across the Canadian Arctic, has been accelerating towards Siberia for the past 2 decades. It's now moving at roughly 50 kilometers per year, fast enough that navigation systems have to be updated repeatedly just to keep pace. The maps we trust have to chase it. Revision after revision, as the pole drifts ahead of the ink, the world magnetic model, which airlines and militaries rely on for compass-based navigation, we had to be revised early in 2019 because the pole moved farther than the model predicted. This isn't about the pole being in the wrong place. It's about the pole moving faster than it should, and speed matters more than position. A slowly drifting pole suggests a stable system making small adjustments. A pole that's accelerating suggests a system in transition, maybe in distress. It's the difference between a car easing into the next lane and a car swerving because the driver lost control. And this is where the old assumptions begin to crack. For decades, scientists pictured magnetic reversals as slow, orderly processes unfolding over thousands of years. The dipole weakens gradually. The poles wander, and eventually, after a long transition, north and south trade places. Symmetry was part of that story. The field thins evenly. The reversal proceeds with a certain patience, and life on Earth barely notices. But what if the field doesn't weaken evenly? What if it fractures asymmetrically, opening weak zones while the pole drift accelerates at the same time? What if the system doesn't have thousands of years to flip, but decades? That isn't gradual change. That's threshold behavior, the moment a hairline crack in ice becomes a sudden fracture. When a tipping point is crossed, the whole system can reorganize violently. Scientists have a word for systems like that: nonlinear, like avalanches, like feedback loops, like a river suddenly changing course. And nonlinear systems don't send gentle warnings. They send accelerating signals right up until the moment they fail. Earth's magnetic field is starting to show those signals. The South Atlantic anomaly is expanding. The North Magnetic Pole is sprinting towards Siberia. The magnetosphere is taking longer to recover from solar storms. These aren't isolated curiosities. They're symptoms of a system under strain. And the strain isn't coming from only one direction, because while Earth's internal magnetic engine wobbles, the Sun is doing something it hasn't done in a long time. Part 3. The Sun's 11-year wrench. The Sun flips its magnetic poles every 11 years like clockwork. North becomes south. South becomes north. With a regularity so steady, scientists can often predict it down to the month. Solar cycle 25. The current cycle was expected to be quiet. Models suggested it might be one of the weakest cycles in a century, a cosmic lull that would ease our space weather worries. Instead, solar cycle 25 has turned into one of the most active cycles on record. Sunspot counts have blown past predictions. Solar flares are clustering in patterns the forecasts didn't expect. The Sun isn't behaving the way it should, and researchers are working overtime to understand why. Let me slow down and explain what a solar cycle really is, because it isn't just about sunspots. Deep inside the Sun, magnetic field lines are twisted and tangled by churning plasma. The Sun doesn't rotate as one solid body. Its equator spins faster than its poles, so magnetic lines get wrapped around it like rubber bands around a ball. This creates toroidal magnetic fields, loops of magnetism coiled through the Sun's interior. As those loops build tension, they eventually punch through the surface, forming sunspots and releasing energy as solar flares and coronal mass ejections. Every 11 years, the Sun's magnetism gets so tangled it resets. The poles flip, the toroidal fields unwind, and the cycle begins again. This is normal. It's been happening for as long as we've watched the Sun. But solar cycle 25 is showing signs of what some scientists call toroidal turmoil. The magnetic loops aren't unwinding smoothly. They're snapping chaotically, releasing bursts of energy that run beyond what the models predicted, like tension letting go all at once. Two spacecraft, Solar Orbiter and Parker Solar Probe, are giving us unprecedented views of this behavior. Parker Solar Probe dives closer than any mission in history, skimming through the corona and measuring magnetic fields directly. Solar Orbiter images the Sun's poles, regions we've never seen this clearly before, and both missions are telling the same uneasy story. As if we finally turned on the lights in a room that was already moving. The Sun's magnetic field is more chaotic than expected. Field lines cross and reconnect, generating sudden releases of energy. The solar wind is gustier, more turbulent. carrying stronger magnetic disturbances out into the solar system. And this matters because the Sun and Earth are magnetically coupled. When the solar wind reaches Earth's magnetosphere, it doesn't simply bounce away. It compresses the shield, distorts its shape, and injects energy into it. Strong solar storms can trigger geomagnetic storms on Earth. That's what happened in May 2024. But what if the coupling goes deeper? What if repeated compression events, hammering the magnetosphere through an unusually active cycle, transfer stress inward? What if the external battering from the Sun starts to destabilize Earth's internal magnetic dynamo? This is speculative, and I'm flagging it clearly. There's no direct evidence solar storms can cause pole reversals. Reversals begin inside Earth. Driven by the motion of liquid iron in the outer core, the Sun doesn't control that process. But here's the uncomfortable question. Could the Sun influence the timing? Could an exceptionally strong solar cycle, arriving when the internal dynamo is already weakened and unstable, act like a rhythmic hammer, pushing the system over an edge it was already nearing? Think of it like a spinning top that's starting to wobble. You don't need one massive shove to knock it over. You only need small nudges at the right moments, in rhythm with the wobble, until stability finally gives way. The energy required is tiny compared to the energy already in the system. It isn't about brute force. It's about timing. And solar cycle 25 isn't over. The peak usually comes 4 to 5 years into a cycle, which means we're still in the rising phase. More storms are coming, bigger ones. Likely, and when solar cycle 25 ends, solar cycle 26 begins. Scientists are already watching with quiet concern because the Sun's magnetic behavior is growing less predictable. If the magnetosphere is showing structural fatigue, and if the internal dynamo is already wobbling toward instability, then the next few cycles aren't just space weather. They're stress tests. And the question isn't whether the Sun can flip Earth's poles. The question is whether the Sun can be the nudge that tips an already unstable system into a transition. Part 4. Why a solar storm could be the trigger. Let's be plain, solar storms do not cause magnetic pole reversals. They don't have the energy. They don't reach deep enough. Reversals originate more than 900 kilometers beneath your feet, in the churning outer core of liquid iron that generates Earth's magnetic field. That dynamo is driven by heat from the core, by the planet's rotation, by convection currents we can't see and barely understand. It's an engine that has run for more than 3 billion years. An ancient machine humming in darkness on scales that make solar storms look like mosquito bites. But triggers aren't the same as causes. A trigger is a small event that destabilizes a system already primed to fail the spark in a room full of gasoline. The final straw. If Earth's magnetic dynamo is already weakened, already wobbling, already edging toward a reversal, then the Sun's forcing doesn't have to be huge. It only has to arrive at the right moment. Here's what we do know about the dynamo. The outer core is liquid iron, roughly the temperature of the Sun's surface, spinning and convecting in complex patterns. As this conductive fluid moves through existing magnetic fields, it generates electric currents, and those currents generate more magnetic fields. It's a self-sustaining feedback loop called the geodynamo, and it's remarkably sensitive to changes in flow patterns. Small shifts in how the iron moves can amplify over time, creating large-scale changes in the magnetic field at Earth's surface. The dipole field, the familiar two-pole structure, is only one possible configuration of the geodynamo. It's stable when flow patterns in the outer core stay organized in a particular way. But if those patterns are disrupted, if turbulence grows, if convection turns chaotic, then the dipole can collapse. The field doesn't vanish. It reorganizes into a multipolar state, with several smaller magnetic nodes instead of 2 dominant poles. And eventually, after a period of instability, the dynamo settles back into a dipole configuration, but with the poles reversed. This is an internal process. It doesn't need outside help. Still, this is where external forcing becomes relevant. The magnetosphere, Earth's magnetic shield in space, is connected to the dynamo below. When the magnetosphere is compressed by a solar storm, that compression doesn't only affect the space environment, it propagates through the system. Energy is transferred into the ionosphere, into the upper atmosphere, and some scientists suspect it could even influence flow patterns in the outer core through something called magnetospheric ionospheric thermospheric coupling. This idea is speculative and controversial. Most geophysicists will tell you the energies are far too small to matter, that the outer core is too deep and too isolated for surface magnetic disturbances to affect it. But a growing number of researchers point to correlations between high solar activity and changes in Earth's magnetic field patterns that don't fit internal processes alone, at least not cleanly. They aren't claiming the sun causes reversals. They're suggesting the sun might modulate the timing. Think of pushing someone on a swing. You don't need to push hard, you push at the right moment. In rhythm, and the amplitude builds if the sun delivers repeated geomagnetic storms, each compressing the magnetosphere and injecting energy. And if those storms arrive while the dynamo is already unstable, then the cumulative effect might be enough to nudge the system toward a transition it was already approaching. This is threshold behavior. Systems far from a tipping point are resilient. You can hit them hard and they absorb the shock. Systems near a tipping point are fragile. The smallest perturbation can push them over, and the signs suggest Earth's magnetic field may be close to such a point. Field strength has been declining for centuries. The South Atlantic anomaly is expanding. The poles are accelerating. These aren't the fingerprints of a stable system. They're the fingerprints of a system in transition. So when scientists say reversals aren't overdue, they're technically correct. Reversals don't follow schedules. There's no cosmic timer ticking down to the next flip. But that doesn't mean we're safe. It means we're in a danger window, a period of elevated risk. And we don't know how wide that window is, or when it closes. We can't see the edge from where we're standing. We only feel the tilt. It could be decades. It could be centuries. Or it could be the next solar storm. And if the trigger does arrive, if the dynamo tips into reversal, then we're not talking about a simple swap from north to south. We're talking about a collapse phase, a period when Earth has no dipole field at all, a time when the magnetosphere fragments into a chaotic mosaic of localized magnetic nodes, a time when the word north loses its meaning. And every compass becomes a question. Part 5, long overdue, is the wrong phrase. You've probably heard it 1,000 times. Earth's magnetic poles are 780. 000 years overdue for a reversal. It gets repeated in documentaries, articles, and social posts, because it feels like a simple countdown. It sounds authoritative. It sounds urgent, and it's misleading. Reversals don't run like train schedules. They don't arrive every 780. 000 years with German punctuality. The interval varies wildly across Earth's history. Sometimes reversals come every 100. 000 years. Sometimes millions of years pass without one. The last reversal, the Brunhes-Matuyama event, was about 780. 000 years ago. But that doesn't mean the next one is late. It only means we've been in a long, stable stretch. And long, stable stretches don't last forever. Here's what does matter. Reversal rates speed up during some epochs and slow down during others. When you look at the paleomagnetic record, Earth's magnetic history preserved in rocks and sediments, you see clusters, periods of frequent reversals followed by long, quiet spans. And crucially, those clusters correlate with times when the field was weak. Weak fields reverse more often. That fits the dynamo picture. A strong, stable dipole resists perturbations. A weak, chaotic field is easier to flip. And right now, Earth's magnetic field is weakening at about 5% per century. That doesn't sound dramatic, but it accumulates. Over the past 2,000 years, the field has lost roughly 30% of its strength. We're not at the historic lows yet, but we are moving in that direction. And there's another wrinkle: geomagnetic excursions. These are episodes where the field weakens dramatically and the poles wander erratically. But the dipole doesn't complete a full reversal. The field becomes chaotic for a few hundred or a few thousand years, then restabilizes with the same polarity it began with. Excursions are more common than full reversals, and they occur more often during times of low field strength, we're already inside a danger window. And that's the part worth taking seriously. Declining strength, asymmetric weakening, and accelerating pole motion together place us in a configuration that historically precedes either a reversal or an excursion. We don't know which. We can't predict it. But long overdue distracts from the real issue, vulnerability, the fragile hinge. The whole story turns on, closer than the word overdue ever admits. Tonight, we simply listen. It isn't about a countdown. It's about living in a state where the system is primed to fail, and we don't know what will finally push it over the edge. It's the hush of a loaded spring quiet. Patient, not yet released. Geological records show reversals can arrive suddenly. The transition from a stable dipole to a multipolar tangle doesn't always take thousands of years. Some entries in the paleomagnetic record show field changes unfolding within a human lifetime. In the most chaotic phases, the poles can wander hundreds of kilometers in a single year. This isn't speculation. It's written into volcanic rocks that locked in the field's direction at the instant they cooled and hardened. So if someone asks whether we're overdue, the answer is no. But if they ask whether we're at risk, the answer is unequivocally yes. And the risk isn't only the reversal itself, it's what happens during the transition, during the collapse phase, when Earth's magnetic field stops behaving like a shield and becomes a fragmented, restless network of localized poles that can't protect us the way we're used to. Here's the part nobody trains for. During a reversal, Earth doesn't have two poles, it has many. And that multipolar Earth is a planet we have never had to live on before. Part 6. The multipolar Earth nobody prepares for. Imagine waking up one morning and checking your compass. The needle drifts and spins, unable to commit to a direction. You open your phone's compass app. Same confusion. You search online and find millions of people reporting the same quiet. Uncanny failure. For a moment, it's as if the planet itself is searching for a center it can no longer hold. Compasses everywhere, from pocket tools to billion-dollar navigation systems, become useless at the same time. North isn't north anymore. It isn't south either. It's simply absent. This is what happens when Earth's dipole field collapses. The single dominant two-pole structure that has held for hundreds of thousands of years fractures into a multipolar configuration. Instead of one North Pole and one South Pole, you get 4, 6, maybe 8 smaller magnetic nodes scattered across the globe. Like faint lanterns scattered under the skin of the world, these nodes drift over months and years. They strengthen and weaken unpredictably, and none of them are strong enough to produce the organized, planet-spanning field we're accustomed to. Navigation fails first, and it fails completely. Every compass-based system from maritime shipping to aviation rests on the assumption that there's a stable magnetic north somewhere near the geographic North Pole. When that assumption breaks, the infrastructure built on top of it starts to buckle. Airlines can't rely on magnetic headings in the usual way. Ships can't trust compasses for course correction. Even GPS, which doesn't use magnetism to calculate position, leans on magnetic calibration for orientation. Your phone knows which way you're facing because it has a magnetometer inside. In a multipolar transition, that sensor turns into nonsense. Humans can adapt to navigation problems. Eventually, we have other ways to find direction stars. Inertial guidance. Radio beacons. We can relearn old skills and build new ones. What we can't adapt to as easily is the loss of magnetic shielding. A multipolar field doesn't just confuse compasses, it can weaken the magnetosphere to a fraction of its normal strength. Here's why. The magnetosphere's shape and reach depend on a strong dipole field. Those field lines arc out into space, forming a protective bubble that deflects solar wind and cosmic rays. In a collapse, that bubble draws inward, closer to the atmosphere, like a shield tightening around a sleeping Earth. When the dipole collapses, the lines fragment into localized loops that don't extend far from the surface. The magnetosphere shrinks, the shielding capacity drops, and suddenly Earth is exposed to radiation levels it hasn't faced in 780. 0.000 years. But before we get to radiation, we need to talk about duration, because this isn't a quick flip. Paleomagnetic records suggest the multipolar phase can last anywhere from a few hundred years to several thousand centuries. Plural, multiple human lifetimes. Long enough that people born during the collapse phase could live their entire lives on a planet with no reliable magnetic north. And long enough for the uncertainty to feel ordinary. Long enough that entire civilizations could rise and fall before the field restabilizes. And when the dipole finally reforms, there's no guarantee the new North Pole will be anywhere near the old one. It could emerge over the Pacific. It could settle near Antarctica. The geographic North Pole, the axis of Earth's rotation, stays put, but magnetic north becomes a wanderer. Every map, every navigation system, every assumption about planetary orientation has to be rewritten, and animal migrations begin to falter. Birds, sea turtles, whales, and countless other species navigate using Earth's magnetic field. They have magnetoreceptors that sense field lines and use them like internal compasses. When the field goes multipolar, those compasses break. Migratory species get lost. Breeding populations fail to reach their destinations. Ecosystems that depend on migration for nutrient cycling and pollination start to unravel. This isn't apocalyptic storytelling. This is biology. We know animals use magnetoreception. We know they depend on stable field geometry. And we know that during past reversals, species experience stress. The fossil record shows disruptions in migratory species during periods of magnetic instability, not necessarily extinctions, but disruptions, bottlenecks, range shifts, evolutionary pressure. Humans, of course, don't navigate by magnetoreception. We navigate by technology. And during the multipolar phase, that technology doesn't behave the way it's supposed to. Which brings us to the real danger, the thing that keeps scientists awake when they think about magnetic reversals in the modern era. We're more dependent on the magnetosphere than any civilization in history, and we've built our infrastructure on the assumption that it will always be there. It won't, and when it fades, the radiation begins. Part 7. Zero Shield. The radiation reality. Let's clear up a misconception right now. Losing Earth's magnetic field does not mean instant death. It doesn't mean the surface gets scoured like Mars. It doesn't mean oceans boil away. Earth's atmosphere provides substantial radiation shielding on its own, and the atmosphere isn't going anywhere during a reversal. You can step outside during a multipolar phase, and you won't immediately collapse, but you will live under higher radiation than any human generation in recorded history. The danger is cumulative, more like a faint drizzle that never quite stops than a single dramatic strike. And over time, that matters. Cosmic rays are high-energy particles, mostly protons, born in supernovae and other violent events across the galaxy. They travel near the speed of light, and when they meet Earth's magnetosphere, many get deflected. Field lines funnel them toward the poles, which is why auroras favor the Arctic and Antarctic. The magnetosphere acts like a shield, keeping most cosmic rays away from the equator and mid-latitudes where most humans live. When the magnetosphere collapses, that shield thins. Cosmic rays that would normally be turned aside reach the upper atmosphere at all latitudes. They collide with nitrogen and oxygen, producing showers of secondary particles, muons, neutrons, gamma rays. Some of those particles make it all the way to the surface, and some pass through your body. The dose isn't apocalyptic. It's not Chernobyl. It's more like a permanent, low-level rise in background radiation, like living at high altitude, where exposure is already higher because there's less atmosphere above you. Airline pilots and flight attendants live with this today. In some countries, they're classified as radiation workers because their cumulative exposure over a career exceeds the general population. During a magnetic reversal, everyone becomes an airline crew member in terms of exposure. Even at sea level, cancer rates rise, mutation rates increase. Fetuses are more vulnerable to developmental harm. In public health terms, small percentages become real people. These effects are statistical, not immediate. You won't feel the radiation. You won't see it. But across a population of 8 billion, even a small risk increase translates into millions of additional cases. And it's not just humans. Every organism on Earth gets the same dose: increased plants, animals, microbes. Ecosystems already stressed by climate change and habitat loss now face elevated mutation pressure. But cancer is a long-term problem. The immediate crisis is infrastructure. Satellites feel the radiation first, and satellites are the quiet backbone of modern civilization. GPS, communications, weather forecasting, military operations, financial transactions. So much of it depends on satellites. And satellites are fragile. Each one is a small city of electronics, sealed in metal, doing delicate work in an unforgiving sky. Cosmic rays can cause single-event upsets, glitches, where a high-energy particle flips a bit in memory or damages a semiconductor. Usually, shielding keeps these events rare, but during a magnetic reversal, the rate of single-event upsets can skyrocket. Operators watch error logs fill like silent snowfall. Satellites malfunction more often. Some fail completely. And because there's no robust magnetosphere to protect them, replacing failures becomes far harder. Launch windows are constrained. Radiation damage begins the moment a new spacecraft reaches orbit. The constellation we built over decades degrades faster than it can be replaced. And then there's the ozone layer. Cosmic rays interact with the upper atmosphere in ways that break down ozone molecules. The mechanism is well understood. High-energy particles create nitrogen oxides that catalytically destroy ozone. During past magnetic reversals, ice core data shows spikes in atmospheric nitrogen compounds, evidence that ozone depletion was underway. The ozone hole over Antarctica, the one linked to CFCs in the 20th century, would look quaint compared to a full reversal. Less ozone means more ultraviolet reaching the surface. UV doesn't just cause sunburn. It damages DNA. It disrupts photosynthesis in phytoplankton, the base of the ocean food chain. It increases cataracts and suppresses immune systems in animals. The feedback loop is brutal. Cosmic rays thin ozone. More UV gets through. And ecosystems already stressed by radiation face another pressure. But even this isn't the worst part. Radiation is survivable. Ecosystems are resilient. Life on Earth has endured reversals before and continued on. The real existential threat isn't biological. It's civilizational. While radiation accumulates slowly, the infrastructure that keeps 8 billion people alive can fail much faster, and it starts with the power grid. Part wit. Grid death isn't the scary part. This is where the story shifts from sky to street, from physics to everyday life. When a geomagnetic storm hits, it doesn't only paint the sky with auroras, it also induces electric currents in the ground. These are geomagnetically induced currents, or GICs, and they are a nightmare for power grids. Here's the mechanism. Fluctuations in Earth's magnetic field create fluctuations in the electric field at the surface. Long conductors like power lines act like antennas, converting those fluctuations into currents. Those currents flow into transformers, and transformers are not designed to handle direct current. They're designed for alternating current at 60 Hz. They hum happily on AC. DC makes them choke. Dump DC into a transformer and you saturate the magnetic core. Generate heat. And if the current is strong enough, you can melt it. Extra high voltage transformers, the massive units that step power up for long-distance transmission, are especially vulnerable. They're custom built, weighing hundreds of tons, and there are no warehouses full of spares. If a major EHV transformer is destroyed, it can take a year or more to build and install a replacement. And during a reversal, when the field is weaker and more chaotic, even modest geomagnetic disturbances can trigger GICs strong enough to do damage. The March 1989 Quebec blackout is the classic example. A moderate geomagnetic storm induced currents strong enough to knock out the Hydro-Quebec grid. 6 million people lost power in about 90 seconds. The blackout lasted 9 hours. If the storm had been stronger, if more transformers had failed, the outage could have stretched for months. And that happened when Earth's magnetic field was comparatively strong. During a reversal, the same storm could be orders of magnitude worse. But here's the twist. Grid failure isn't the scary part. Blackouts are reversible. You can restart a grid. You can reroute power. The scary part is permanent infrastructure loss. When transformers fail in a reversal-era world, they can't be replaced quickly because the supply chain that manufactures them depends on electricity. You need power to run the factories that build transformers. You need power for the transportation systems that deliver them. And if the grid is down for months, those factories aren't running. Those delivery systems aren't operating. Cascading failure begins here. Lose the grid, and you lose water pumping stations. Cities rely on electric pumps to move water from reservoirs and treatment plants. No power. No water. Within days, sanitation crises spread. Lose the grid, and you lose fuel distribution. Gas stations can't pump without electricity. Refineries can't operate. Diesel generators, the backups meant to keep critical systems alive, run out of fuel and fall silent. Lose the grid, and you lose communications. Cell towers have batteries, but those batteries last hours, not days. Internet infrastructure depends on powered routers and servers. Without electricity, the digital world goes dark. And in a crisis, when coordination and information are everything, that blackout makes every other problem worse. But even this isn't the true bottleneck. The bottleneck is logistics. Modern civilization doesn't run on stockpiles. It runs on just-in-time delivery. On the assumption that trucks, trains, and ships are always moving, always resupplying, and just-in-time logistics require GPS, fuel, electricity, and communication, all of which depend on a functioning grid and a functioning satellite network. Markets, medicine, and meals all ride on that invisible coordination. When those systems fail, you don't get a temporary disruption. You get a reorganization of society. Cities become difficult to inhabit. Supply chains fragment into local networks. The global economy, the web of trade that feeds 8 billion people, splinters into isolated regions that must become self-sufficient. This is the part nobody likes to say out loud. The part dismissed as doomerism. But it's a question that has to be asked. If the grid goes down and stays down, if the logistics network fails, how many people can the planet support without modern agriculture and distribution? The answer, based on pre-industrial levels, is somewhere around 1 billion, maybe less. Part 9. The 180-day logistics cliff. Modern agriculture isn't just farming, it's manufacturing. Fields aren't plowed by hand, or even by simple tractors. They're managed by GPS-guided systems that plant seeds with centimeter precision, apply fertilizer at variable rates based on soil data, and harvest with combine machines that cost more than most houses. Every step from planting to distribution depends on electricity, fuel, and data. Fertilizer production depends on natural gas for the heat process, the reaction that converts atmospheric nitrogen into ammonia. That process runs in massive industrial plants that operate continuously. Shut them down, and restarting is expensive and time-consuming. No fertilizer means crop yields drop by half or more. Modern high-yield agriculture exists because we add synthetic nitrogen to soil. Without it, we fall back to the carrying capacity of natural fertility, which supported far fewer people. Fuel is the other dependency. Tractors, harvesters, irrigation pumps, transport trucks, most of it runs on diesel. And diesel comes from refineries that require electricity and crude oil. If refineries shut down, diesel supplies dry up within weeks. Farmers can't plant, they can't harvest, and even if they could, they can't reliably move food into cities. Cities are the most vulnerable nodes in the system. Urban populations don't produce their own food. They import it from rural areas through a logistics network that moves millions of tons of food every day. That network depends on refrigeration, which depends on electricity. It depends on trucks, which depend on fuel. It depends on routing and coordination, which depend on GPS and communications. Break any one link, and the food doesn't arrive. Sometimes, Even a brief blackout in data is enough to stall the chain. Grocery stores carry about 3 days of inventory. Panic isn't required for the math to work. Distribution centers carry about a week. After that, cities run out of food, not some food, all food. And there's no cavalry coming. The just-in-time system has no redundancy, no buffer, no plan for what happens when the entire supply chain stops moving for months. Water systems fail next. Urban water infrastructure is a marvel of engineering reservoirs. Treatment plants, pumping stations, miles of pipe, all synchronized to deliver clean water on demand. But it's entirely dependent on electricity. Without power, pumps stop. Treatment plants can't operate. Within days, cities lose running water, and once taps run dry, sanitation collapses, disease spreads, and mortality among vulnerable populations, infants, the elderly, the immunocompromised spikes. This is why 6 months is a critical threshold. 6 months, roughly 180 days, is how long many experts estimate it takes for urban populations to face catastrophic collapse if the grid stays down and logistics remain broken, not because people instantly starve, but because cascading failures in water, sanitation, and disease control reach a point where cities become unlivable. There's a grim idea nicknamed the 90% casualty scenario, suggesting that if the grid and logistics fail for a sustained period during a reversal, 90% of urban populations in developed nations could die within a year. This is speculative. It's based on models, not direct data. Because we've never had a civilization this dependent on electricity experience a prolonged blackout. But the models aren't wild guesses. They're grim spreadsheets of dependency, not prophecy. They're built from known dependencies, known failure modes, and historical examples of what happens when supply chains break. The carrying capacity argument is uncomfortable, but straightforward. Before the Industrial Revolution, before synthetic fertilizer and mechanized agriculture, Earth supported about 1 billion people. We're at 8 billion now. That 7-fold increase is powered by fossil fuels and industrial technology. If that technology stops working, if we lose the ability to produce food at industrial scale and distribute it globally, then carrying capacity falls back toward pre-industrial levels. 7 billion people don't fit into that equation, and a reversal that lasts centuries, keeping the grid unstable and logistics fragmented, creates exactly that scenario, not overnight, not theatrically, but slowly over months and years as cities empty and populations move toward regions that can still produce food locally. This isn't speculation about reversals existing. It's speculation about what happens if we can't maintain industrial civilization through one. And that question hinges on one thing: whether we can keep the grid running through repeated geomagnetic disturbances, whether we can adapt infrastructure to a world without a stable magnetosphere, because if we can't, then the reversal isn't just a geological event, it's a civilizational bottleneck. And the next question becomes, has Earth seen anything like this before? Have previous excursions coincided with collapses in complex life, or in human populations? The answer is maybe, and the evidence is buried in ice. Part D's. The forbidden question: has this happened before 42,000 years ago? Earth's magnetic field nearly collapsed, not a full reversal, but close. The event is called the Lachamp excursion, sometimes linked to what's been called the Adams event, and it's preserved in ice cores, tree rings, and sediments around the world. Field strength dropped to less than 10% of what it is today. The poles wandered erratically across the planet, and for about 1,000 years, Earth had almost no magnetic shielding. This is not speculation. This is data. Volcanic rocks from that period record chaotic field directions. Ice cores from Greenland and Antarctica contain spikes in beryllium-10 and carbon-14, isotopes created when cosmic rays strike the atmosphere. Those spikes indicate cosmic ray flux rose dramatically during the Lachamp excursion. Exactly what you'd expect if the magnetosphere weakened. What makes the Lachamp excursion especially interesting is timing. 42,000 years ago overlaps with a period of significant ecological and cultural change. Neanderthals went extinct around this time. Cave art blooms in Europe and Southeast Asia, vivid animals. Handprints, abstract symbols painted deep underground. Megafauna populations crashed. Climate became unstable, not because magnetism changed the weather directly, but because increased cosmic rays may have altered atmospheric chemistry, cloud formation, and precipitation patterns. Scientists are careful not to draw neat causal arrows. Correlation isn't causation. And other factors could explain Neanderthal extinction and megafauna decline competition with Homo sapiens. Climate shifts tied to the Ice Age. Still, the timing is striking. The Lachamp excursion is the most recent large-scale magnetic shielding collapse, and it coincided with a period of profound biological and cultural upheaval. And here's where it gets strange. Oral traditions from indigenous cultures around the world contain stories about the sky changing, about the sun behaving erratically, about a time when stars moved in unfamiliar patterns. Australian Aboriginal stories describe a time when the sky was broken. Norse mythology speaks of Ragnarok, a season of cosmic chaos before renewal, as if the night itself is remembering. Mesoamerican myths describe cycles of creation and destruction tied to celestial events. Are these stories distant echoes of the Lachamp excursion? Did humans witness auroras creeping toward the equator? The disorientation of migratory animals, the slow rise of radiation-driven mutations, and then pass it along. This is deeply speculative, and most scientists avoid these connections because the evidence is circumstantial. Myths are not data. Cultural memory is unreliable, but it's hard to ignore how widespread sky disaster stories are the recurring theme of upheaval followed by renewal. If Earth's magnetosphere stayed weak for 1,000 years in recent prehistory, humans were there. They experienced it. And if they survived, they remembered. Mutation rates spiked during the Lachamp excursion. Ice core and sediment data show increased genetic diversity in some species during this period, consistent with higher radiation exposure causing more mutations. Most mutations are neutral or harmful, but in a small percentage of cases, they're beneficial and they drive evolutionary change. The Lachamp excursion may have been an evolutionary accelerator, a period when natural selection operated faster because mutation pressure was higher. Humans survived, obviously. We're here, but survival doesn't guarantee thriving. Some genetic studies suggest human populations experienced a bottleneck around this time, a dip in total numbers before recovery. That bottleneck could have been driven by climate, competition, disease, or by a combination of stresses, with magnetic field collapse acting as one more weight on the scale. We don't know. We can't know with certainty. The past is fragmented, preserved in ice and rock and story, and we're trying to reconstruct it from incomplete pieces. But the Lachamp excursion proves magnetic shielding collapses can happen, that they can affect life on Earth, and that they don't necessarily trigger mass extinction, but they do create long periods of instability. If it happened once, it can happen again. And if it's happening now, if Earth is entering another excursion or a full reversal, then we won't be the first humans to face it. We'll simply be the first to face it with industrial civilization, 8 billion people, and technology that quietly assumes a stable magnetosphere. And we're not alone in the threat landscape, because as Earth's field weakens, the space around us is becoming more hostile. The sun isn't the only thing we need to worry about. Part owns. The sun is not acting alone. Earth's magnetosphere doesn't end at a clean boundary where space begins. It extends outward in a teardrop shape compressed on the sunward side, stretched into a long tail on the night side. The edge of this bubble, the magnetopause, fluctuates with solar wind pressure. Beyond it is the heliosphere, the sun's magnetic bubble, extending far past the planets. And beyond the heliosphere is interstellar space, the region between stars filled with gas, dust, and cosmic rays. A vast invisible shoreline where the sun's influence fades. For most of modern science, we treated these as clean divisions, stable boundaries. The sun's influence reaches out to roughly 100 astronomical units. Beyond that lies the interstellar medium, predictable, tidy lines. But recent data from the Voyager probes crossing into interstellar space in 2012 and 2018 suggest those boundaries aren't as stable as we assumed. The heliosphere is shrinking not dramatically, not catastrophically, but measurably. Pressure from the interstellar medium, the gas and magnetic fields between stars, is higher than models predicted. That increased pressure compresses the heliosphere, pushing it inward. It's a slow squeeze, measured in instruments and quiet graphs, not in headlines. And when the heliosphere compresses, it becomes less effective at shielding the inner solar system from galactic cosmic rays. Pause on that for a moment. We're not talking about a local problem anymore. We're talking about our entire solar system inside a protective bubble being squeezed from the outside. The interstellar medium sounds like emptiness, but it isn't empty at all. It's threaded with charged particles, magnetic fields, and radiation from distant stars and supernovae. The heliosphere acts like a windbreak, deflecting much of this galactic weather away from the inner planets. But if that windbreak is pushed inward, if the protective zone shrinks, then its edge creeps closer to us. Voyager 1 and Voyager 2 have been sending back measurements from beyond the heliopause, the boundary between the Sun's influence and interstellar space, since 2012 and 2018, respectively. They are humanity's most distant ambassadors, moving through a region no human-made object had ever touched before. And what they're telling us is unsettling. The interstellar medium is denser than expected. The magnetic pressure is stronger. The transition zone, where the solar wind meets the interstellar wind, is more turbulent. Turbulence means variability. The heliosphere doesn't compress uniformly. It fluctuates. Sometimes it pushes outward when solar activity is high. Sometimes it contracts when interstellar pressure rises. And during contractions, shielding effectiveness drops. Galactic cosmic rays that would normally be deflected tens of billions of kilometers from Earth can penetrate deeper into the inner solar system. This is separate from solar activity. It's a galactic-scale phenomenon. Earth sits inside the Sun's protective bubble, which sits inside the galaxy's broader magnetic environment, and changes at the galactic level can propagate inward. We're not talking about immediate catastrophe. We're talking about a slow increase in background cosmic ray flux that's independent of what the Sun is doing. The Milky Way generates cosmic rays, constantly supernova remnants, pulsars, black holes. These sources accelerate particles to near light speed and scatter them across the galaxy. Our solar system moves through the Milky Way at about 230 kilometers per second, plowing through different regions of the interstellar medium as it orbits the galactic center. Sometimes we pass through denser patches. No sirens, just numbers inching upward as our solar system sails on. Sometimes we enter regions with stronger magnetic fields. And right now, based on Voyager data, we appear to be entering a region where interstellar pressure is higher than it's been in recent millennia. Nobody knows exactly why. The galaxy is enormous, and mapping its magnetic structure is like charting an ocean from a single boat. But the trend is measurable. The heliosphere is under more pressure now than when we first began studying it in the 1,970 seconds. If that trend continues, if we're drifting into a harsher radiation neighborhood, then Earth's magnetosphere has to work harder to keep us safe. And here's the compounding factor: if Earth's magnetic field is weakening while the heliosphere is compressing, we lose shielding from two directions at once. The heliosphere deflects cosmic rays from the galaxy. The magnetosphere deflects what makes it through, like nested shields around a fragile world. When both weaken simultaneously, exposure increases multiplicatively, not additively. This is what keeps some scientists awake at night. It's not one problem, it's a convergence of problems. The Sun's magnetic cycle is unusually active. Earth's magnetic field is declining. The heliosphere is compressed. And the galactic environment is growing more hostile. Any one of these factors alone would be manageable. Together, they suggest Earth's radiation shielding is being eroded from multiple angles at once. Galactic cosmic rays are more energetic than solar particles. They penetrate deeper. They can do more damage. Solar particles are mostly protons, with energies in the millions of electron volts. Galactic cosmic rays can reach energies in the billions, sometimes even trillions of electron volts. When they strike the atmosphere, They don't just create a few secondary particles. They create full cascades, showers of muons and neutrons and gamma rays that spread like a cone, reaching all the way to the surface. And they are always present. A constant background rain of high-energy particles the heliosphere normally holds at bay. During solar storms, the radiation flux spikes for hours or days, then returns to baseline. Then the long, quiet rain resumes patient as distant starlight. But galactic cosmic rays don't stop. They don't pass. They persist, quietly relentless. And if the heliosphere's shielding capacity is slipping even a little, and Earth's magnetosphere is slipping too, then we're entering a season of elevated cosmic ray exposure that has nothing to do with reversals or solar storms. It's simply unlucky timing. The sun happens to be in an active mood. Earth's field happens to be weakening. The heliosphere happens to be compressed. None of these factors alone is catastrophic. Together, they sketch a world that's more vulnerable to space radiation than it has been in millennia. Some researchers are digging into historical cosmic ray records preserved in ice cores and tree rings, searching for eras when the flux ran unusually high. What they're finding is subtle but provocative. Cosmic ray intensity tracks solar activity the way we expect, yet it also shows longer-term swings that the solar cycle can't explain by itself. There are decades-long, even century-long stretches when cosmic ray flux stays elevated, even during solar minimum. When the sun is comparatively quiet, those periods appear to line up with times when the heliosphere was likely squeezed when the solar system drifted through denser regions of the interstellar medium. We might be entering one of those periods now. Detectors on the ground, in orbit, and at high altitude have been showing an upward trend over the past 20 years. It isn't dramatic. It isn't the kind of spike that triggers alarms, but it's steady. And steady is what matters when exposure accumulates over years and decades. The biological effects of chronic, low-level radiation are well studied. Cancer risk rises. Mutation rates tick upward. Cellular repair systems get taxed and, in some cases, overwhelmed. For humans living at sea level, the increase is small enough to vanish into the background noise of everyday radiation. But for astronauts, for high-altitude populations, for people who live in the sky on long flights, the dose stacks up, layer by layer. And if the trend continues, if cosmic ray flux keeps climbing as the heliosphere compresses and Earth's field weakens, then eventually it becomes a public health issue. But we're not there yet. We're in the early phase, where scientists publish careful papers, present cautious slides at conferences, and debate whether the signal is real or just statistical shimmer. The public doesn't hear much about it because it's slow. It's subtle. It doesn't feel like a threat you can point to. But the direction of the data is hard to ignore. Cosmic ray flux has been rising. The heliosphere is under more pressure, and Earth's magnetic field is declining. These are observations, not storytelling. Scientists are hesitant to speculate about galactic influences on Earth because the timescales are immense and the mechanisms are still hazy. We don't know how long this heliospheric compression will last. We don't know whether we're entering a harsh neighborhood for centuries or brushing past a temporary ripple. We don't know how much a higher cosmic ray background will shape life on Earth, because we've never measured it during a period when both the heliosphere and the magnetosphere were simultaneously weakened. What we do know is simple. The universe is not a safe place. Earth's habitability depends on stacked layers of protection: the atmosphere, the magnetosphere, the heliosphere. Remove one layer and life becomes harder. Remove two, and you begin approaching the edge of what complex ecosystems can comfortably tolerate. And if a magnetic reversal weakens the magnetosphere for centuries while the heliosphere remains compressed, we will be testing planetary resilience in ways we've never had to test before. And if you want to see what it looks like when a planet loses its magnetic protection for good, you don't need to wait for Earth. You only need to look at Mars. Part 2's Mars as a warning, not a comparison. Mars used to have a magnetic field billions of years ago. Mars had a molten core, a dynamo, and a magnetosphere that helped protect its atmosphere from the solar wind. Then the core cooled, the dynamo faded, and over millions of years, the solar wind stripped away most of Mars's atmosphere. leaving the thin, cold, radiation-soaked world we see today. This is what the MAVEN mission Mars Atmosphere and Volatile Evolution has been studying since it arrived in 2014. MAVEN measures how the solar wind interacts with Mars's upper atmosphere, and the evidence is unambiguous. Mars is still losing atmosphere, not fast, but steadily. Every second, roughly 100 grams of Martian air escapes into space, carried off by the solar wind. Over geological time, that steady leak becomes fate. Mars went from rivers and lakes to a frozen desert because it couldn't hold its air without a global magnetic shield. The process is called atmospheric escape, and it comes in several forms. For Mars, one of the most important is ion pickup. Solar wind particles slam into the upper atmosphere with tremendous energy. They collide with atmospheric molecules, knock electrons loose, and create ions. Those ions are charged, and charged particles respond to magnetic fields. The solar wind carries its own magnetic field. When those field lines sweep past Mars, they can grab the newly formed atmospheric ions and drag them outward into space. MAVEN can watch this in real time. Its orbit carries it through the upper atmosphere and out into the solar wind, like a probe skimming the boundary between a planet and the void. On each pass, it measures the density of escaping ions, the strength of the solar wind, and the magnetic configuration, and what the data shows is brutally simple. Without a global field to deflect the solar wind, Mars's atmosphere is being sandblasted away, particle by particle, second by second, year after year. 100 grams per second doesn't sound like much, about the weight of a candy bar, but multiply it by the number of seconds in a year, and you get about 1 million kilograms over 1,000 years, and far more over the deep sweep of time. Mars's current atmospheric mass is only about 25 trillion kilograms total. The planet has already lost most of what it once had, and the process has not stopped. Earth will not become Mars. Let's be clear, Earth's core is still molten. The dynamo is still running, even if the dipole collapses during a reversal. It will eventually reorganize and return. Mars's loss is permanent. Earth's reversal is temporary, but the lesson still matters. The mechanism of loss is the same. When there's no strong magnetic field to deflect it, the solar wind can erode the upper atmosphere. On Earth, during a multipolar phase, the magnetosphere weakens to a fraction of its normal strength. An atmospheric loss can accelerate. Not enough to notice in a single lifetime, but over centuries. The math becomes meaningful. Earth's atmosphere is vastly more massive than Mars's. We have about 5 quadrillion kilograms of air wrapped around the planet, held by stronger gravity and replenished by volcanic outgassing and biology. Losing a few billion kilograms during a reversal wouldn't put a dent in the whole. But the upper atmosphere, the thermosphere and exosphere, where satellites live, is more vulnerable. These layers are already thin, and they're the first to feel what increased solar wind exposure can do. The ionosphere, a charged layer from about 80 to 600 kilometers up, is especially important. It reflects radio waves, enabling long-distance communication. It shapes GPS signals. It's where auroras glow. And it's directly affected by solar wind pressure. During geomagnetic storms, the ionosphere gets disturbed, creating scintillation that degrades satellite links and GPS accuracy. During a magnetic reversal, when shielding is diminished and the solar wind has more direct access, the ionosphere could become chronically unstable. MAVEN has also shown that stripping intensifies during solar storms. When a coronal mass ejection hits Mars, the loss rate spikes. The solar wind punches deeper, ionizes more particles, and carries them away. MAVEN measured roughly a 10-fold increase in atmospheric escape during a strong solar storm in 2015. The spike lasted for days, and when the storm passed, Mars had lost far more atmosphere than it would have during a quiet interval. If Earth experiences repeated solar storms during a magnetic reversal, the same kind of amplification can happen here. The atmosphere doesn't vanish, but it can be eroded, especially in the upper layers where satellites orbit and where the ionosphere normally helps our signals travel. Each storm takes a bite. Each coronal mass ejection pulls away more ions, and across the decades and centuries of a reversal, those small bites add up. And here's the uncomfortable parallel. Mars didn't lose its atmosphere overnight. It happened gradually, over immense spans. While the planet may still have been partly habitable, there could have been a long interval, hundreds of thousands of years, when Mars had liquid water on the surface, even as its magnetic protection weakened. Geology suggests lakes, rivers, perhaps even an ocean in the northern lowlands. The water didn't vanish the moment the field faltered. It took time. Life, if it existed, would have experienced rising radiation, a thinning sky, and a climate losing its balance. The earliest changes would have been quiet, more cosmic rays reaching the ground, more UV slipping through as ozone chemistry shifted, a slow drop in atmospheric pressure. If microbes lived in Martian lakes 3 billion years ago, they might have had centuries or millennia to adapt before the surface became truly inhospitable. And eventually Mars crossed a threshold. The atmosphere grew too thin to support stable surface water, and the planet froze. Water either escaped or locked itself into polar ice and subsurface permafrost. The climate settled into the cold desert state we see now, and it happened because the magnetic field died, and once it was gone, there was no global mechanism left to slow the loss. Earth is not crossing that same threshold during a reversal. Our atmosphere is thicker, our gravity is stronger, our core still generates magnetism. Even if the surface field becomes temporarily chaotic and weak, but the direction of the physics is similar. Lose magnetic protection, even temporarily, and you accelerate upper atmospheric erosion. And if reversals become more frequent, if Earth enters a long epoch of repeated excursions, like some periods in the geological past, then the cumulative effect becomes a genuine long-term concern. The geological record includes eras when Earth's field reversed every 100,000 years, sometimes even more often. Those eras lasted millions of years. If we're entering something similar, if today's instability is the opening note of a longer pattern, then slow upper atmosphere erosion becomes part of the story. Even if it's invisible day to day. Not for us. Not for our children. But for civilizations hundreds of thousands of years from now, who might look back and wonder why the sky is slightly thinner than it once was. And there's another lesson from Mars that is more immediate. MAVEN data shows that remnant magnetic fields, localized patches in the Martian crust, create small pockets of partial protection. Ancient minerals locked in magnetism billions of years ago. And those faint fields still deflect some particles today. The protection is minimal, but measurable. Escape rates are slightly lower over these crustal anomalies. Earth's South Atlantic anomaly is the inverse, a place where the field is weaker, not stronger. But the principle is the same. Magnetic field strength matters locally, not only globally. During a multipolar reversal, when Earth carries several weak nodes scattered across its surface, some regions will have better shielding than others. Living under a stronger node could mean lower radiation exposure and fewer ionospheric disruptions. Living between nodes, in a magnetic dead zone, could mean taking the full brunt of solar wind effects. Geography becomes destiny in a way it hasn't been since humans first learned the importance of shelter. Where you are on Earth during a reversal could shape how much radiation you absorb, how stable your upper atmosphere behaves, how badly your technology degrades. And unlike climate zones, which shift slowly, magnetic nodes can drift over years and decades. Safe zones would move, and people would follow them. Mars is a warning about what happens when protection is lost permanently. Earth's reversal is temporary, but temporary can still mean centuries. And across those centuries, every solar storm, every cosmic ray shower, every geomagnetic disturbance chips away at the systems that keep us comfortable, connected, and alive. But we aren't facing this blind. We're building tools to detect subtle changes early, to predict space weather more precisely. And some of those tools are beginning to notice patterns humans can't easily see. Part trees. AI discovers patterns humans miss. Machine learning is exceptionally good at finding correlations in large data sets. It's less good at explaining why those correlations exist, but it's excellent at noticing when something is drifting away from baseline quietly, persistently. Before a human analyst would feel confident calling it real, space weather prediction is almost tailor-made for this. We have decades of magnetometer readings, satellite measurements, solar observations, all stored in enormous archives. A human can spot the obvious features on a plot-sharp spikes, broad trends, periodic swings, but subtle changes that develop over months or years, relationships between variables that don't look connected at first glance, those are harder to catch by eye. The limitation isn't intelligence, it's scale. The data sets are vast and multidimensional. One magnetometer station produces thousands of readings per day. Multiply that across hundreds of stations worldwide. Add satellite streams from dozens of spacecraft. Add solar observations from ground-based telescopes and space missions, and you're dealing with petabytes of information. No human mind, no matter how trained, can hold more than a thin slice of that at once. To recognize patterns across such volume, you need computational brute force algorithms that sift through millions of points, hunting correlations that span weeks or months, and interactions that look unrelated until the statistics quietly reveal a thread. And that is exactly what machine learning excels at. AI doesn't get bored. It doesn't blink. It doesn't miss something because it's tired. Feed it the data, and it will flag anomalies, odd couplings, deviations from the expected norm. And over the past few years, AI-driven analysis of space weather has been identifying patterns that scientists are still working to interpret. One example is especially intriguing. Models trained on historical geomagnetic storm data have found patterns in magnetospheric recovery time that correlate with long-term field strength. Storms that occur when the background field is weaker tend to recover more slowly, which matches theory. But the models also suggest something else. Recovery time appears influenced by the intensity of the previous storm, hinting at a memory effect, as if the system doesn't fully reset between hits. That's genuinely surprising. The magnetosphere is dynamic, constantly reshaped by solar wind pressure and the interplanetary magnetic field. Conventional wisdom held that after a storm, the system returns to baseline within a day or two. Essentially independent of what came before, each storm was treated as discrete, like striking a gong. It rings, then settles, then the next strike begins fresh. But the AI models are suggesting something more haunting. They imply the gong never fully stops ringing before the next strike arrives. If that's true, then storms during active solar periods when events arrive in quick succession aren't independent at all. They're cumulative. Each one leaves a trace, a slight weakening, making the system more vulnerable to the next. This wasn't the expectation. It wasn't a clean prediction from theory. It's a pattern the algorithms surfaced, and now the human work begins, trying to find the physics beneath it. Is there a process where residual disturbances from one storm shape the next response? Maybe plasma trapped in the magnetosphere lingers longer than expected. Maybe field line topology remains subtly distorted for days or weeks. Maybe energy stored in the radiation belts leaks forward, amplifying later storms. Or maybe it's a mirage, a statistical artifact. Machine learning can find patterns that aren't real, especially in noisy data. Maybe it's seasonal variation in solar wind speed. Maybe it's calibration drift in instruments. Maybe the pattern exists, but we're telling the wrong story about it. Nobody knows yet. But the fact that AI can detect these signals before humans can explain them is both powerful and unsettling, because it means we may be relying on black box warnings about changes we don't fully understand. The AI says the magnetosphere is behaving abnormally. It can't tell us why. It only knows the pattern is wrong. This is the central limitation of current machine learning approaches: deep neural networks. The algorithms driving most of these discoveries are essentially sophisticated pattern-matching engines. They learn by example, tuning millions of internal parameters until they can accurately reproduce the training data. But they do not build physical models. They do not understand causation. They can tell you that X is correlated with Y with 99% confidence. But they can't tell you why X and Y are related, or whether the relationship is fundamental or coincidental. This creates an ethical, practical dilemma. Do we act on AI warnings even if we don't understand the underlying cause. Do we wait for human scientists to catch up and verify the findings? And what happens if the AI detects a pattern that suggests an imminent reversal? But the pattern is built on correlations we can't explain. Picture this scenario. An AI model trained on centuries of paleomagnetic data and decades of modern magnetometer readings flags a specific combination of indicators: rapid pole acceleration plus asymmetric field weakening plus slow magnetospheric recovery plus increased cosmic ray flux. The model says this combination has only occurred twice in the geological record, and both times it preceded a reversal within 50 years. The confidence level is 85%. What do you do with that knowledge? Do you sound the alarm and start preparing for a reversal that might not happen? Do you dismiss it as an AI hallucination and risk missing the one chance to prepare? Do you invest billions in grid hardening and satellite redundancy based on a correlation you don't understand? There's no right answer. And this is where human judgment has to fill the gap. Scientists are beginning to develop hybrid approaches using AI to identify interesting patterns and then designing targeted experiments and observations to test whether those patterns reflect real physical processes. It's a feedback loop. AI finds anomaly. Humans investigate. Findings refine the AI model, which finds new anomalies. And the cycle continues. Early success stories suggest we should listen. AI models predicted the May 2024 storm's intensity more accurately than traditional models. They flagged the magnetosphere's slow recovery before human analysts noticed it. These systems are proving useful, even when they're not perfect. The May storm is actually a perfect case study. Traditional space weather models use physics-based simulations. They take solar wind measurements from spacecraft positioned between the Sun and Earth, plug those measurements into magnetohydrodynamic equations, and predict how the magnetosphere will respond. These models are powerful, yet they struggle with extreme events because the equations become nonlinear and chaotic at high energies. AI models don't care about the equations. They just learn from past storms. And because the training data included several G5 storms from previous solar cycles, the AI recognized patterns in the solar wind data that indicated an extreme event was incoming. It didn't know why those patterns meant a major storm. It just knew that historically, when those patterns appeared, strong storms followed. The AI forecast was right. The physics-based models underestimated the storm's intensity by 30%, and when the magnetosphere took 5 days to recover instead of 2, the AI models flagged it immediately because the recovery curve didn't match any previous storm in the training data. Human analysts might have noticed eventually, but the AI caught it in real time. But AI is also a mirror. It reflects the data it's trained on. And if the data contains biases or gaps, the AI inherits them. If we don't have enough data from past reversals, which we don't, then AI can't reliably predict what a reversal looks like. It can only tell us when today's behavior deviates from recent history. This is the dataset problem. We have excellent magnetometer data going back about 150 years. We have satellite measurements going back 60 years. We have paleomagnetic data from rocks and sediments spanning millions of years. But we have zero high-resolution data from an actual reversal or excursion. The Lachamp event happened 42,000 years ago, and our records from that period are indirect isotope ratios in ice cores, magnetic orientations in volcanic rocks, nothing close to the temporal and spatial resolution we'd need to train an AI model properly. So AI models trained on modern data are optimized for detecting anomalies within the range of recent behavior. They can tell us when things are different from the last century or two. They can't tell us whether those differences indicate an imminent reversal or just natural variability because they've never seen a reversal. And recent history is a poor guide when the system is entering a state it hasn't been in for 780,000 years. This doesn't mean AI is useless. It means we need to be honest about its limitations. AI is an early warning system, not a prediction engine. It can alert us when something unusual is happening, but it can't tell us what will happen next. That interpretation still requires human expertise, physical understanding, and the willingness to make decisions under uncertainty. Still, AI is watching, quietly, like a stethoscope pressed to the planet. It listens for the faintest tremor in the field. Satellites are monitoring. Scientists are analyzing. We're building a surveillance network around Earth's magnetic field, trying to catch the early warnings of a collapse that we know is possible, but can't predict. Magnetometer stations on every continent. Spacecraft measuring the solar wind. Ground-based observatories tracking sunspots. And AI algorithms processing it all in real time. Looking for the patterns that humans might miss, the network is getting denser. Quietly, new satellites launch every year. More ground stations come online. The data streams grow larger and more detailed, and the AI models get trained on increasingly sophisticated data sets, learning to recognize subtler anomalies to distinguish signal from noise with greater accuracy. But while we watch Earth, we're also watching the space around Earth. Because the threats aren't just planetary anymore, they're orbital, and they're multiplying. Part 14. Part 14. The satellite graveyard problem. There are more than 9,000 active satellites orbiting Earth right now. Thousands more are planned for deployment over the next decade, mostly in low Earth orbit, where they circle the planet every 90 minutes. These satellites provide GPS, internet, weather monitoring, communications, military surveillance, scientific observation. Modern life depends on them, and they're all vulnerable to space weather. During geomagnetic storms, Earth's upper atmosphere heats up and expands. This increased atmospheric drag affects satellites in low orbits, pulling them downward. Usually, satellites can compensate with onboard propulsion, firing thrusters to maintain altitude. But during a prolonged period of magnetic instability during a reversal, the atmosphere stays expanded, drag increases permanently, and satellites start deorbiting faster than they can be replaced. The mechanism is simple, but brutal. When a geomagnetic storm hits, it injects energy into the upper atmosphere. That energy heats the thermosphere, the atmospheric layer between 80 and 600 kilometers altitude, where most satellites orbit. Hot gas expands. The atmosphere puffs up like a balloon, extending higher into space. And satellites that were comfortably above most atmospheric effects suddenly find themselves plowing through thicker air. Air resistance at orbital speeds is no joke. A satellite moving at 8 kilometers per second experiences drag forces that gradually slow it down. The orbital velocity decreases, the orbit decays, and the satellite spirals closer to Earth. Modern satellites carry propellant specifically for altitude maintenance. They fire thrusters periodically to boost themselves back up, compensating for the drag. But propellant is finite. Always. Once it runs out, the satellite becomes a dead weight falling toward Earth. This is not hypothetical. After strong solar storms, satellite operators routinely report increased drag and shortened orbital lifetimes. Some satellites have to be abandoned early because they run out of fuel trying to maintain altitude. And these are isolated events. Single storms. During a reversal, the storms don't stop. The atmospheric expansion becomes baseline. Pause and think about what that means. For centuries, possibly millennia, Earth's upper atmosphere remains in a chronically expanded state. Every satellite in low orbit experiences continuous elevated drag. Propellant consumption rates double or triple. Satellites designed to last 15 years burn through their fuel in 5. And because launching replacements during a reversal is more difficult and expensive, the satellite population starts to decline. The International Space Station, orbiting at roughly 400 kilometers, requires regular reboosts to maintain altitude even during quiet space weather. During solar cycle 25, the station has needed more frequent boosts than predicted because atmospheric drag has been higher than models expected. If that elevated drag became permanent, the ISS would require constant resupply missions just to keep it aloft, and eventually the cost would become unsustainable, and the station would be abandoned to burn up in the atmosphere. Now scale that problem across 9,000 satellites. Every Starlink satellite, every GPS satellite, every communications relay, every Earth observation platform, all of them fighting the same battle against atmospheric drag, all of them burning through propellant faster than designed, all of them facing shortened operational lifetimes. Now add another problem: Kessler syndrome. This is the scenario where the density of objects in orbit becomes high enough that collisions create debris, which causes more collisions, which creates more debris in a runaway cascade. We're not at that threshold yet, but we're close. And if satellites start deorbiting uncontrollably during a reversal, if operators lose the ability to maneuver them safely, then the collision rate spikes. Here's how the cascade works. A satellite loses propellant and can't maintain altitude. It starts drifting. Another satellite tries to maneuver around it, but misjudges the trajectory. Collision. Both satellites shatter into thousands of pieces. Each piece becomes a projectile traveling at orbital velocity. Sedum to awesome Kim, S. At that speed, a paint chip can penetrate a spacecraft hull. A bolt can destroy a satellite. Those thousands of debris fragments spread out along the orbit. Within days, they form a ring of shrapnel circling Earth. Other satellites pass through this ring. Some get hit. More collisions. More debris. The ring grows denser, and once the collision rate exceeds the natural debris removal rate, which happens when objects fall into lower orbits and burn up in the atmosphere, the process becomes self-sustaining. Once Kessler syndrome begins, it's self-sustaining. Debris fields grow. Orbital lanes become unusable. And launching new satellites becomes impossible because anything you send up gets shredded by debris within weeks. Low Earth orbit becomes a graveyard, permanently inaccessible. The mathematician Donald Kessler, who first described this scenario in 1978, calculated that once orbital debris density exceeds a critical threshold, the cascade becomes irreversible on human timescales. Natural atmospheric drag will eventually clean up low Earth orbit, but the process takes decades to centuries depending on altitude. A debris cascade at 400 kilometers might clear in 10 years. A cascade at 800 kilometers might take a century. During a magnetic reversal, when we can't safely launch new satellites, when existing satellites are failing faster than normal, and when orbital debris is accumulating, we could cross the Kessler threshold without any chance of recovery until the reversal ends. And by then, the damage is done. Low Earth orbit is unusable. The satellite infrastructure is gone. Lose the satellites, and you lose GPS. Navigation systems fail. Precision agriculture stops. Shipping routes become inefficient. Aviation has to revert to ground-based navigation, which is slower and less reliable. You lose weather monitoring. Hurricane predictions become less accurate. Climate models lose real-time data. You lose communication. Remote regions that depend on satellite internet go dark. Military coordination degrades. GPS alone touches nearly every aspect of modern life in ways most people don't realize. Precision farming uses GPS to guide tractors within centimeters, optimizing seed planting and fertilizer application. Power grids use GPS timing signals to synchronize electrical transmission across regions. Financial markets use GPS timestamps to sequence trades. Emergency services use GPS to route ambulances and fire trucks. Shipping companies use GPS to track cargo worldwide. All of this vanishes if the GPS constellation fails. Weather satellites are even more critical than most people understand. Hurricane prediction depends on continuous satellite monitoring of ocean temperatures, atmospheric moisture, and storm system development. Without satellites, we lose 3 to 5 days of hurricane warning time. Tornado warnings become less accurate. Severe weather forecasting reverts to ground-based radar and surface observations, which can't see developing systems until they're already dangerous. Climate science takes a catastrophic hit. Decades of continuous Earth observation data tracking ice sheet melting, sea level rise, deforestation, atmospheric composition, ocean temperatures. All of it depends on satellite measurements. Lose the satellites, and we lose the ability to monitor planetary-scale environmental changes. We go blind at exactly the moment when understanding climate dynamics becomes critical for survival. The economic impact is staggering. Estimates suggest the satellite industry is worth over $400 billion. But that's just the direct value. The indirect value, the industries that depend on satellite services, is orders of magnitude higher. Lose the satellites, and you don't just lose space infrastructure. You lose a foundational layer of the global economy. Banking and financial systems rely on satellite communications for international transactions. Supply chain management depends on satellite tracking of ships and trucks. Television and radio broadcasting use satellites for distribution. Internet infrastructure in remote areas depends entirely on satellite links. The entire digital economy, worth trillions of dollars globally, has satellite dependencies woven throughout its architecture. And here's the worst part. You can't rebuild it. Not during a reversal. Not while the magnetosphere is weak and the atmosphere is expanded and the radiation environment is hostile. Any new satellite you launch has a shortened lifespan, higher failure rate, more vulnerability to single-event upsets. The cost of maintaining a satellite constellation during a reversal becomes prohibitive. Launch costs are already high, typically tens of millions of dollars per satellite when you factor in manufacturing, launch vehicle, insurance, and ground operations. If satellites are failing 3 times faster than normal, you need to launch 3 times as many to maintain the same constellation size. And if the radiation environment is causing electronics failures, you need radiation-hardened components, which are heavier and more expensive, which means bigger launch vehicles, which means higher costs. The math doesn't work. At some point, the cost of maintaining satellite infrastructure during a reversal exceeds the economic benefit and the market collapses. Commercial operators abandon unprofitable constellations. Government agencies cut satellite programs to free up budget for more immediate crisis. And gradually, over years or decades, the satellite population declines to a tiny fraction of what it was. We're facing the possibility of permanent orbital isolation. A planet where space is temporarily inaccessible, not because we lack the technology, but because the environment won't allow it. And once that window closes, once the debris field forms and the orbital lanes become unusable, we're stuck on the surface for generations until the field restabilizes and the debris naturally deorbits. This is a new kind of existential risk unique to technological civilizations. Ancient humans didn't need satellites. They survived reversals without GPS, without communication networks, without weather monitoring. But we've built a world that can't function without these systems, and we're about to test whether that world can survive their loss. The dependency runs deeper than convenience or economic efficiency. Modern agriculture, the system that feeds 8 billion people, depends on GPS-guided equipment and satellite weather forecasting. Remove those tools, and crop yields decline. Global food production drops, and we're back to the logistics cliff. The carrying capacity problem, the question of how many people Earth can support without industrial technology. Emergency response systems collapse without satellites. When hurricanes hit with less warning, when earthquakes can't be monitored from space, when wildfires spread faster than ground-based detection can track them, the death toll from natural disasters skyrockets. Coastal populations become more vulnerable. Disaster relief becomes less effective. And the cumulative mortality over years and decades adds up. Military capabilities degrade across the board. Modern warfare depends on satellite reconnaissance, GPS-guided munitions, and secure satellite communications. Without these capabilities, conflicts become bloodier and less precise. Strategic stability declines because nations can't verify arms control agreements without reconnaissance satellites. The risk of miscalculation increases. This is civilization being stress-tested in real time. Every system we've built, every assumption about global connectivity and real-time information gets challenged simultaneously. And the stress doesn't end when the reversal stabilizes, because the reversal will end. The field will stabilize. North and south will settle into new positions, but the world that emerges from the multipolar phase won't be the world that entered it. Part Keynes. After the flip, the world that rebuilds. Eventually, the chaos ends. The multipolar field, with its scattered nodes and wandering poles, settles back into a dipole. North and south re-establish themselves, though not necessarily where they were before. The magnetosphere reinflates. Cosmic ray flux drops back to normal levels. The radiation pressure eases, and Earth, battered but intact, begins to stabilize. Geological records suggest this process takes anywhere from a few hundred years to a few thousand years. The Lachamp excursion lasted about a millennium. Other reversals in the paleomagnetic record show durations, some as brief as a century or two. We don't know where on that spectrum the next reversal will land. We don't know if it will be a full reversal or just an excursion. But eventually it ends. The transition from multipolar chaos back to dipole stability isn't sudden. It's gradual, uneven, marked by false starts and temporary regressions. The magnetic field might strengthen for a decade, giving the appearance of restabilization, then weaken again as the dynamo undergoes another convective reorganization. Magnetic nodes that seemed permanent might dissolve. New ones might appear in unexpected locations. And throughout this entire process, which could span 10 or 20 human generations, civilization has to operate without the assumption of a stable north. But eventually, the system finds equilibrium. The flow patterns in the outer core settle into a configuration that supports a stronger pole field. One magnetic node grows dominant, suppressing the others, and becomes the new North Pole. Another node at the opposite end of the planet becomes the new South Pole. The field lines stretch out into space. The magnetosphere reforms, and Earth once again has the protective bubble it's had for hundreds of thousands of years. The new pole positions are unpredictable. Magnetic north might end up in the Pacific Ocean. It might end up in Africa. Geographic north. The axis of rotation stays the same, but magnetic north becomes a new reference point. And every navigation system, every map, every compass has to be recalibrated. This recalibration is more than a technical inconvenience. It represents a fundamental reorientation of how humans understand planetary geography. For centuries, we've used magnetic north as a navigational reference. Compasses point north. Maps are oriented with north at the top. Aviation charts, maritime routes, hiking trails, all of them reference magnetic headings. When magnetic north moves to a completely different location, all of that infrastructure becomes obsolete. Hang navigation charts have to be redrawn. Runways are designated by their magnetic heading rounded to the nearest 10 degrees. Runway 18 means it points roughly 180 degrees magnetic, which is south. If magnetic north shifts to the Pacific Ocean, that same runway might now point 120 degrees magnetic, making it runway 12. Every airport in the world needs new markings, new charts, new approach procedures. Maritime navigation faces similar challenges. Shipping routes have been optimized over centuries based on magnetic variation. The difference between true north and magnetic north at any given location, when the poles flip, magnetic variation maps become worthless. Sailors and ship navigation systems have to relearn the magnetic landscape of the entire planet, charting new declination values for every ocean and coastline. Even hiking and wilderness navigation transforms. Trail markers, orienteering courses, search and rescue protocols, all of them assume a certain magnetic configuration. When that configuration changes, people get lost more easily. Rescue operations take longer. And in the immediate aftermath of the reversal, when the new pole positions are still being precisely determined, there is a period of genuine navigational uncertainty, when even experts aren't completely sure which way magnetic north points. Climate shifts. 2. The magnetosphere's shape influences atmospheric circulation in subtle ways, and changing the pole positions changes those patterns. Some regions get wetter, some get drier. Ocean currents, driven partly by wind and partly by Earth's rotation, adjust to the new magnetic configuration. These changes aren't catastrophic, but they're disruptive. Agricultural zones shift. Coastal areas experience different storm patterns, and civilizations that survive the reversal now have to adapt to a planet that's subtly different from the one they knew. The mechanisms are complex and not fully understood. The magnetosphere affects where auroras occur, and auroras deposit energy into the upper atmosphere at high latitudes. That energy influences atmospheric circulation, creating or suppressing jet stream patterns. During a reversal, when auroras appear at all latitudes unpredictably, this energy deposition becomes chaotic, and when the field restabilizes with poles in new locations, the aurora zones move. The energy deposition patterns shift, and the atmosphere adjusts to a new equilibrium. Ocean currents respond to changes in wind patterns and thermal gradients. The Gulf Stream, the current that keeps Europe warmer than it would otherwise be, depends on specific wind patterns and temperature differences between the tropics and the poles. If those patterns shift even slightly, the Gulf Stream might weaken or change course. Western Europe could become colder. Fisheries that depend on specific ocean temperatures might collapse or migrate to new regions. Monsoon patterns, which billions of people depend on for agriculture, are sensitive to atmospheric circulation changes. A shift in the magnetosphere's configuration could alter monsoon timing or intensity, turning previously fertile regions into marginal farmland, and vice versa. The Indian subcontinent, Southeast Asia, and Sub-Saharan Africa, all regions where monsoons are critical, would face agricultural unpredictability for generations as the new climate patterns establish themselves. Migration follows climate. People drift toward the places that stay kind, and away from landscapes that turn dry or unstable, like coastlines on a chart being quietly redrawn. It isn't a sudden stampede. It's a slow reweaving across generations, a quiet reorientation of where families settle, where fields can grow, and how communities endure. After the flip, the atlas of human civilization cities, borders. Even the idea of normal regions looks unmistakably different. Coastal cities already strained by sea level rise and storm surge take on extra risk when storm tracks shift. A coastline that once feared hurricanes only as distant news may begin seeing them as regular visitors. Seawalls built for one climate rhythm stop matching the new tempo. And because the reversal has already drained attention and materials, the capacity to adapt is limited. Even agricultural heartlands begin to shift. The American Midwest, the breadbasket many nations lean on, depends on familiar rainfall, timing, and growing seasons. Change those inputs and yields fall. Farmers respond with new crops, new schedules, new irrigation, and sometimes the hard decision to abandon marginal land. But adaptation is not instant. And in the in-between years, food production dips. Northern regions once too cold for intensive farming may become workable ground Siberia. Northern Canada, Scandinavia, people move toward newly habitable zones, but roads, storage, clinics, rail, and ports aren't waiting there at scale. Building the farms, towns, and transport webs that can support large populations takes decades. The global distribution of population, relatively stable for centuries, undergoes a slow rearrangement. With that rearrangement come tensions, politics that harden, resources that feel scarce, and borders redrawn to match new demographic gravity. Technological regression becomes likely, not because humans forget, but because complex systems need steady foundations to stay complex. It isn't a fall back to the Stone Age. It's a step down from peak interconnectedness. Industries dependent on satellites, stable grids, and global logistics either transform or fade. Some tools persist: wind, hydro, local agriculture, basic manufacturing. Others struggle: semiconductor fabrication, with its clean rooms and constant power demands, becomes brutally difficult to maintain. The internet, built on continuous electricity and long-haul links, fractures into smaller islands or vanishes in some regions entirely. This is the quiet collapse, not explosions, not movie scenes, but the slow sanding down of complexity until society reaches what it can reliably carry without the machinery we lost, like signals fading under a deepening, man-made fog. It becomes a world where certain things simply stop working, and people adapt by living simpler, harder lives. The semiconductor industry is a perfect illustration. Modern chip fabrication requires facilities that cost billions to build and operate. These fabs need stable electricity, ultra-pure water, particle-counted clean rooms, and supply chains pulling specialized materials from dozens of countries. One extended outage can ruin months of production. A contamination event can shut a fab for weeks. During a reversal, keeping those conditions becomes near impossible. Grids wobble, shipping stutters, parts arrive late or not at all. And even if you keep a fab running, demand collapses because the device's chips power smartphones, computers. Advanced vehicles can't be manufactured at scale without the same steady infrastructure. The internet doesn't disappear overnight, but it splinters. Undersea fiber optic cables, carrying most international data, rely on powered repeater stations every 50 to 80 kilometers. Those stations need electricity. When grids fail, international connectivity drops. The internet balkanizes into regional networks that connect only intermittently. Unable to sustain the always-on global presence we treat as normal, social media, cloud computing, streaming, all of it leans on vast data centers that consume staggering power. Without reliable electricity, services degrade, then shut down, their server halls going from a steady hum to a rare, uncertain flicker. The digital economy contracts to a fraction of its former size. Regional survivability varies wildly, and the difference is often as simple as whether lights stay on and food keeps moving. Countries with robust local food production, decentralized energy, and low population density fare better. Iceland, with geothermal power and a small population, might feel disruption as inconvenience rather than collapse. Dense megacities dependent on imported food and centralized infrastructure face catastrophic losses. The global hierarchy reshuffles into a new order based on resilience and self-sufficiency. New Zealand, with isolation, agricultural capacity, and renewable resources, becomes a kind of haven. Scandinavian countries, practiced in harsh seasons and invested in distributed infrastructure, to adapt more successfully than nations built around a single brittle spine. Small island nations with strong traditions of fishing and local farming may endure, while megacities that import 90% of their food unravel. The geopolitical order transforms. Nations powerful for their technological edge lose influence. Nations that kept agricultural self-sufficiency and energy independence gain it. And the survivors, the communities that make it through the reversal intact, begin rebuilding a different kind of civilization. One that prizes redundancy and repair. Human adaptation is what we do best. We've lived through ice ages, volcanic winters, pandemics, wars. We survived the Lachamp excursion 42,000 years ago. Even if memory of it is faint, we can survive the next reversal too, if it comes. But survival isn't continuity. The civilization that emerges from a magnetic reversal won't be the same civilization that entered it. And here's the final uncomfortable truth. We might be better prepared than we think, just not in the way we like to measure. We aren't ready for grid failure, satellite loss, or prolonged radiation stress. But psychologically, we function inside uncertainty. We adapt. We rebuild. We make meaning. And then we keep going. Humans normalize the abnormal with startling speed. Within a generation, children born during the reversal will know nothing else. And they'll learn new instincts for direction and distance without ever thinking to call it loss. They'll grow up without GPS, without global internet, without the assumption of a stable magnetic north. And to them, that world won't feel diminished. It will simply be the world. They'll craft new technologies tuned to that environment, new social systems suited to localized economies, new stories that explain why the sky sometimes glows with auroras at noon, and why the old maps lie. Earth's magnetic field has reversed hundreds of times. Life has persisted through all of them. The planet is resilient. The biosphere is resilient. And humans, fragile as we are, dependent as we are resilient too, especially when the rules change slowly enough for adaptation to catch up. But the world that rebuilds will be quieter, smaller, harsher, A planet where the assumptions of modernity no longer hold, where 8 billion people can't be sustained, where the comforts of global trade and instant communication become memories. A planet where survival means local resilience, where communities rely on what they can grow, repair, and share nearby, not what they can import from across the world. The reversal isn't the end. It's a reset. And the question isn't whether humanity survives. The question is, what kind of humanity steps out the other side? What stories will they tell about the world before the flip? What technologies will they keep? And which will slip into legend? What kind of civilization can you build on a planet where north becomes south, where the sky itself feels unreliable, and where the only certainty is that nothing stays stable forever? We don't know. We can't know, but if the next solar storm is the trigger, if Earth's magnetic dynamo tips into reversal within our lifetime, then we'll learn, and the world will never be the same.